my name is Samantha and I'm a mathematics major at UNM. Today I will be teaching you how to graph a function using derivatives. Part 1. Identify your equation. First, you want to identify what parent function your equation was created from. This will allow you to identify what basic characteristics you will need to find before finding your first and second derivative. Part 2. Finding the basic parts of your graph. Since I am using a polynomial for this video, y equals x to the fourth minus 8x squared plus 8, I found the degree of my polynomial, the maximum turning points in my graph, end behavior, symmetry, domain, as well as the x and y intercepts and the zeros and their multiplicities. If you'd like a little bit more of an in-depth review about the algebra, go ahead and click the link in my description, and I have a video that goes over how I gathered all this information for the basic parts of my graph. Here are just some tables and charts just to review and as a little bit of a refresher. Part 3. Finding the first derivative. So it's important to understand what the derivative is if you're going to use it to graph. So the derivative is the slope of the tangent line at a point on a curve. So the first derivative test will help us find the slope of the tangent line on our curve of our original function. First derivative test allows us to find the x values that are possible, maximum, and minimums. This works because the tangent lines at our peaks and valleys have a slope of 0. So when we are setting our first derivatives equal to 0, it gives us all the x values that have a slope of 0, therefore telling us where we may have a maximum or minimum. Since these are only possible maximums and minimums, we need to test our x values from the first derivative. We call these numbers our critical numbers. Here is a visualization of the first derivative test. Note that at all these tangent lines, the slope is 0, but not at all of those points do we have a maximum or minimum. So for this graph in particular, if we would have set the derivative equal to 0, we would have got x equals -1, x equals 0, x equals 2, and x equals 3.5. But if we would have tested those values, we would have found that while -1 has a max, 0 has a min, x equals 2 is in fact not neither of those, because the slope is in fact increasing the entire way, so the first derivative won't have a sign change. This is why the first derivative test works. We can find the critical points that may be a max or a min by searching for points with a slope of 0, but by testing those points, we can find if we actually have a maximum or a minimum at those points. Finding the first derivative. So now that we understand what the first derivative tells us, we can go ahead and find our first derivative using the derivative rules, which I have done here. Then we're able to set our derivative equal to 0, like I have done here, and find our critical numbers. So first I factored out the common factor, and then I went ahead and used the difference of squares to go ahead and factor it even more. Setting all of those components equal to 0, I found that my derivative equals 0 when x equals 0, x equals 2, and x equals -2. Therefore, these are my critical numbers. And I personally like to put my critical values on a number line so I can see the effect of the slope change. So since the derivative is negative over here, that means we have a decreasing slope. And then it changes to positive, meaning our slope then changes to increasing. This tells us that at -2 we have a minimum. And then at 0 we have a increasing slope that then changes to decreasing, meaning at 0 we have a max. And lastly, because our slope is decreasing and then that changes to increasing, at 2 we will have a minimum. So this table here shows you how the effect of the sign of our first derivative affects the slope of our original function. Now that we know that we have a max and min at our critical values, we want to plug these x values into our original function. These will give us the corresponding y coordinates to our x values that will then give us the coordinates for where our max and min are on our graph. Part 3. Finding your second derivative. So when we set our second derivative equal to 0, for the second derivative test, we are looking for possible inflection points. Inflection points are when our graph changes concavity. For the concavity of a graph to change, the sign of the second derivative must change. Therefore, we set our derivative equal to 0 because it allows us to find the x values where our concavity possibly changes. If the slope is changing from positive to negative, or vice versa, there must also be a point when the slope is 0 before it changes from one sign to the other. Identifying these points allows us to find the exact point our concavity changes. It's important to note that not all graphs have an inflection point. So similar to the first derivative, this is why we want to test our values. So here I have found my second derivative by simply taking the derivative of my first derivative, and then I have set it equal to 0, factor, I simplified it, and then I have found my x values. I also like to put my inflection points on a number line because I'm a very visual person. So this allows me to see that on the left side of my inflection point, x equals negative 2 over the square root of 3, my graph should be concave up, like so. But on the right side of my point, it should be concave down. And then on the right side of x equals 2 over the square root of 3, I should have another concave up. So since my concavity changes along with my signs, that means that these are both, in fact, inflection points. Recap. What does all this information tell us, and how the heck do we use it to graph? So what we know. So all of this information here, we gathered from just knowing what kind of function we're dealing with. Here, we find that our first and second derivative give us a little bit more specific information about how our graph should look. So on the intervals of negative 2 to 0 and 2 to positive infinity, our function should have an increasing slope. On the intervals of negative infinity to negative 2 and 0 to 2, we should have a decreasing slope of our original function. Therefore, we should have maximum at this point, 0, 8, and a minimum at these points, negative 2, negative 8, and 2, negative 8. Our second derivative tells us that our function is concave down on the interval of negative 2 over the square root of 3 to 2 to the square root of 3. And our function is concave up on the intervals negative infinity to negative 2 over the square root of 3 and 2 over the square root of 3 to positive infinity, meaning we have inflection points at these coordinates here. Keep in mind that these are coordinates on our actual graph, while these are intervals. So now let's graph. So up here, I have noted how the slope is changing, and then over here I have our coordinate values. So these would be our intervals. From my intervals at the top, I know that my slope should be decreasing from negative infinity all the way down to negative 2, and then it goes back up to increasing through my inflection point and my x-intercept. Then it hits my y-intercept as well as my max, travels to decreasing through my inflection point down to my minimum, and back up again. So after graphing, it's always smart to graph with a graphing calculator if you have one, just to double check. And that is our graph. So thank you so much for joining me. I hope you have a good rest of your day.